Today we're finally starting on interiors. So let me show you guys how to create this interior here, and it's all procedurally generated, where if I change the seed, you could see we get different actual room designs, all filled with doors to make sure you get into every single room. And not only that, but if I sample it, you can see each area has its own density of points. So you can actually, from this, already filter out the room that you would like, and based on the density, go ahead and start putting in things in specific rooms. It's probably going to be a long tutorial, so let's get into it right now. So here we are in the project as we left it last time. And what I'm going to do is going to come here to the roof section, and I'm just going to detach the roof. That way we see inside of it and we can actually see everything that's going on. So how does this setup work? Well, we're basically going to first create a data asset that's going to house kind of the size of the rooms, including how many there are, and then using that to create that many random points on every single floor. So let's say there are 3 rooms. That means it picks 3 random points on every single floor. And then based on the size of that room that you've specified, it checks the distance out in each direction in X and Y. It doesn't need to check in Z. And then if it matches, then it sets the density based on that. So effectively we get rectangular, square, or slightly cut up rooms of different sizes. And then based on the amount of rooms you have, you could then take and set the density to be as such. For example, if you have 5 rooms, your densities would be at 0, 0.2, 0.4, 0.6, 0.8, and 1. Because we'll be having 5 rooms plus whatever points that were there originally that didn't make the room count, which is kind of the hallway or other area. Once we get into it, it should make more sense. So let's get right into it. The first thing we're going to be doing is basically grabbing our original spline points, and we need to copy them up. So here in a brand new area, I'm going to right click, grab our original spline points. And then right before I copy them up, I'm actually going to set the densities of all of them to be black or 0. So I'm going to search for set attribute, and then the detail panel for input source 1, instead of last, we want to hit the plus button and select density. And for input source 2, we can drag out of NB and search for create attribute and leave it at 0. You can just leave it as default like this, and this will effectively turn all those points black or 0 density. Then we want to copy them up based on the amount of floors we have. Now over here, we already have this system. We already created this copy point up simple with the amount of floor loops and the wall height. So I'll go ahead and take all of this and just duplicate it down below and plug this in. Now, if I go ahead and sample it with a D key, you can already see we now have all of those original points on the inside, nicely all black at 0 density. Now, when we're picking random points on every floor, I don't want to pick it based off of these points. I want the gap between them to never be really that small anytime. So while you could sample these points, the way I decided to do it is by having another spline sampler basically have a different scale and use that for the distance between the points. Because let's say it picks 2 points right next to each other and it does one room, then the other room might encompass the first room entirely. And there's less of a chance that happening on a full scale. So that's why I'm doing it this way. So right below here, I'm going to search for get spline data, get our original spline, and grab ourselves a spline sampler. Now this spline sampler is going to be on interior. It is going to be unbounded, and it's throwing an area here saying 1 or more rows of the spline interior failed to sample. Ensure the spline points are not overlapping. Don't worry about this. This is a false error. It happens quite a bit. But what we need to modify is this interior sample spacing. What I'm going to do is grab our wall size, and I can grab the actor property from any of the stuff we've done before and duplicate down here. And then I want to multiply it by a certain amount. So I'm going to grab a create attribute, just duplicate it down, plug it into NB. And in this case, let's multiply it by 5. So basically, instead of a distance of whatever you've set, every 5 modules will be a new point. Now, this does mean that when you have a super tiny house, this might not generate any rooms effectively, but if you have a bigger or smaller one, you can actually control this. If you'd like to, you of course can expose it to a blueprint, and then you have even more control of the distance of those points where it selects them. But for my testing, this is kind of a good spot for what I was looking for. Now let's go ahead and open up the spline sampler, and we want to plug the output of this multiply into the interior sample spacing and then close it up. And you can see the error actually has gone away. There's no more error. So it's really odd that it shows up because it's complaining about spline points overlapping, but clearly that's not the problem because changing just the spacing of the points, which has no impact on the actual spline points, made the error go away. So that's why I said, don't worry about it. it's fine. So now we need to create our first new loop. What effectively we need to do is pick those random points, and we do it for every single floor and however many we want to specify. Now to do that, we are going to need the actual data asset, as I said before. So let's actually go ahead and create that now, since we're going to need it right here. So here are my data assets. I'm going to right click and search for struct or structure, and I'm going to select it, and I'm going to call this s_room sizes. Open it up, and here we can add our variables. So I'm going to change the first variable here to be an integer. I'm going to add a variable, and this will automatically set the second one to be an integer, which is exactly what we want. Now you want it to be an integer because you cannot have half of a module, because we're currently creating it by modules that are a certain distance, and you can't really have half a module. So an integer is what we want. I'm going to call the first one half width and the second one half height. So the way this is going to work is it's going to pick a point, and then it's going to check on either side based on that variable. So effectively, it's not really half. It's technically, if you have a center point and you have a value of 2, it'll become 2 up, 2 down, 2 left, 2 right. So effectively it becomes a 5 by 5. So technically not a little under half, but as long as you're kind of aware of that, that should be all you need. And now for the default values, I'm going to set them to be something relatively small. Let's say 2 for both will be the default. Once I have that, I need the primary data assets. So I'm going to right click, get ourselves a blueprint class, and then under all classes, search for primary data asset. Go ahead, select it, and I'm going to call it PDA_room sizes. Go ahead and open it up. And all we need to do here is add a single variable. I'm going to call it room sizes. And the type is going to be s_room sizes that we just created. I'm going to right click on it to convert it to an array. I'm going to make that array exposed by hitting the eye icon on the right. And that's all we kind of need here. And the last thing is to actually create the data asset itself. So I'm going to right click, search for data asset, grab ourselves a data asset. And here we're going to search for PDA room sizes right there. Select it. And now I call this DA_regular room sizes. You have multiple of these and you can easily swap them out. So it's not specifically all room sizes. This is just room sizes for this version. If you wanted to, you could duplicate the data asset and then go ahead and set it up with like 5 rooms or 2 rooms or 3 rooms and all different copies with different variables. And that's kind of the beauty of a data asset, because you can just swap them around really easily. Here's the data asset. I've gone ahead and opened it up, and I'm going to populate it with some rooms. I'm going to give it 5 rooms, let's say, and then I'm going to open all of these up, and I'm going to give them a different value. So I'm going to do a 2 by 3, a 3 by 2, because keep in mind, these don't actually do rotations. So if you wanted to have, let's say, a really long room upwards and a real long room sideways, those would be 2 separate rooms. At the current moment, there is no rotation of it. It's one or the other. So in order to kind of combat that, I make one that's tall, one that's wide. Then I'll make a very tall room by 5 by 2, kind of a large room of 4 by 5, and an extra large room of 5 by 7. Now the order of the rooms matters, as you'll see, because it actually takes the first points and prioritizes them. So you want to have larger rooms down near the bottom and smaller rooms near the top. Once we have this, we're all set up with that. And now I can go back to our actual PCG graph. Under graph settings up top, I can add a new parameter. This is going to be of type PDA_room sizes. I'm going to make it a soft object reference, so that way it doesn't get reset every single time. Now keep in mind, this is a little more expensive under the hood, but the primary use case of this is to just go ahead and create the building and then lock it in and then use it somewhere else. It's not to keep it live in the end. So even if it's slightly more expensive, kind of while it's being used, it is a little more convenient. So keep that in mind. I'll go ahead and rename this to room sizes. And from the drop down, I'll select our DA regular room sizes right there. So excellent. We now have everything we kind of need to continue. So now we need to get a loop for these points that we created. We want to basically copy the points up, but also select only a few of them and randomly. In my loops folder, I'm going to right click and search for PCG and grab ourselves a new PCG graph. And this is going to be my PCG_random points with floors. And now I can grab it, drag it into our graph and create a loop node. Now it's all empty, but that's fine. Double click it to open it up. And now let's start setting it up. Now the output is very simple. The type we're going to need basically is a point. This is all we care about. The pin status of advanced, we're going to set it to be normal. And that's all we need for the output. For the input, I might change the first input to be a point. Instead of advanced, it's going to be required. All pin statuses in everything that is an input, I'm going to be setting to required. So just keep that in mind. So I'm not going to mention it again for every single one, but just know if it's an input, it is set to required. And the reason for that is so that way none of the math breaks as it is kind of needed for it to run and to do all the computations correctly. I'm going to add 4 other pins, and they're all going to be of type attribute set. So under allowed type, select attribute set for all of these. And then for the label, go ahead and copy mine to set one to be floors, one data asset, wall height, and seed. At this point, only thing we need to do is set the floors to be a loop. So I'm going to change floors usage from normal to loop. And that's all we need for this input and output. So the first thing we're going to do is basically recreate the copy of the points. So let's drag out the input, grab ourselves a transform points. We can open it up. And from the offset min, I'm going to drag out and search for make vector attribute and then plug the output into the max as well, just both min and max. And for the vector attribute, I'm going to change from vector2 to vector by default. And now we basically need to move it up based on the wall height, which is why we have this input here. So I'm going to take our wall height and I'm going to multiply it by the index of this loop. So out of NB, I'm going to search for get loop index and we can plug that right through. And this is going to be right into Z. So based on the loops that we're doing, we're going to offset them up, higher and higher. So now we need to pick a few of those points, but a specific number of them. And we can basically do that using a density noise and then filtering it and only taking however many we need out of that entire loop system. So I'm going to drag all this out, search for density noise, and keep in mind that is just an attribute noise node with the density set for the input automatically. And then we go ahead and sort this. I'm going to do a sort points, which gets us our sort attributes node. And our input source, instead of last, I'm going to hit the plus button, and I'm going to do it based on density. So we've effectively randomized all of the points from 0 to 1, and then reordered all of the points. So the one that was actually at 0, 1, 2, and 3 are no longer necessarily at 0, 1, 2, and 3. It is now random. So now we need to only grab however many points we need. From here, I grab ourselves an attribute filter. For our attribute filter, we want to change the operator to be less than. And we want it to be less than because if you want to grab 1 point, you actually need index 0. So there's always one less than whatever number you specify. And the target attribute that we want, instead of last, we want index. And now we need to know how many points we're getting. Now we want to do it based on this data asset. If we have 5 rooms, it should pick 5 points. If we have 3 rooms, it should pick 3 points. And we don't want to manually do this every single time. We just wanted to grab that information automatically. So from our data asset, I'm going to drag out and search for get property from object path. Now the property name is going to be room sizes, which is what we've called it here in our data asset. And now there's a nifty new node that I learned about, which is get entries count, which gets us the number of entries in this data asset. So we can just take this and plug that right into the filter. So no matter how many points it had before, it will stop once it reaches this count. But we also have this information now in here. We have all the room sizes. We kind of want to add it and keep track of it. We don't want to do it later since we're already here. So from our get property from object path, I'm going to drag out of here and search for match and set attributes. Instead of this plugging into the in node, I'm going to move it into the match data. I'm going to drag it up, and this is going to be inside filter into in. And then the match and set attributes out can go into the output finally. So whatever information we had here, we now are saving those room sizes the same way. So that's wonderful. But this will make it so it's the same in every single floor because we're doing the same noise, the same sorting, etc. We want to randomize this noise by the floor. So let's open it up. And here we have access to the seed. So I don't want to plug the seed in directly because I want to change by the floor. So what I'm going to do is grab our loop index and we're just going to add to it our seed. And then we're going to plug that into the seed of the attribute node and close it up. So let's say the loop is at 0 and our seed is at 0. First one will be at 0. Second one will be at 1, 2, 3, 4 because it's going by the index. But by actually adding on our own seed, we can offset it. Otherwise, it would always be the same seed on the same floors every single time we did this. So this is just an offset for the seed. But that's all we need for this graph here. So let's go ahead and plug things in. The out points are going to the in. The floors is the floor loops we had before they were created. Let's search for floor loops, plug in that into the floors. Now the data asset is actually the room sizes that we created here. So I'm going to right click and search for room sizes, plug that data asset into our data asset slot. And then we need the wall height and the seed. So I grab our seed and our wall height from from above, in this case from the quarter pillar, but it's available all over the place that we used it. Duplicate down here and then plug both of these in. Now with our point sample, you can see that we are getting these points right here. 1, 2, 3, 4, 5. Now again, you can see that the distance between them is relatively even, and that's because of the multiplication that we have set up. If it is a bit too far, I can change this original value here from 5 to, let's say, 4. And you can see these points are now a little bit closer. So depending on your setup, you might want to have these exposed and control it for your needs. But like I mentioned before, I'll go ahead and keep it on 5 because that seems to work well for what I'm doing. And if I want a different points here, I can go ahead and change the seed to, let's say, 1, 2. And you can see the densities are changing, the positions are changing. Now this whole setup took me quite some time and some effort to get going. So if you're enjoying the tutorial, I would love it if you hit the like button and subscribe if you're new for more awesome tutorials like this. Now that we have these points, this is great, but I also want to actually set the density on these guys based on the amount of points they have. Basically, instead of setting the density later, when we actually have all the points going through, I want to do it on these few points per floor. So every single floor needs to have a density of basically however many points, in this case 5, and we're taking the point loop basically that we're making of each point there and dividing it by 5. So it's going to be 1 divided by 5, 2 divided by 5, 3 divided by 5, effectively resulting in a 0.2, 0.4, 0.6, 0.8, and 1, effectively meaning that every single one of these points will have its own density, and that density will repeat on every single floor, but it will never have multiple of them on the same floor. So here in our loops folder, I'll go ahead and create another PCG graph. This is going to be our PCG underscore set density. Just like before, I'm going to drag it in and create a loop node with it and open it up. Just like before, the output is set to point and normal, and our input is set to be a loop point and as well as a normal attribute set. And for the label on the second one, I'll name it number of points. From here, we just need to set the density. So I'll drag out of this point and search for set, and we want the set attribute math operation. For the input source 1, we want to select density because we want to set the density of this entire thing. And now we need to do it based off of the floors. So the way we do that is by dragging out a number of points and search for modulo, but plug that into B. And from A, we want to get loop index. So every time it goes through the floor and all the points, it resets the value back down. But this will result us, if we had 5 points, and a value from 0 to 4. We actually want it to be between 0 and 1 and decimal points. So we need to take this modulo and divide it then by the number of points again. Now be careful with this. In the divide, you want to force op to be double. If you don't do this, it will output an integer, which means all of your points will become 0 density because they'll probably be rounded down. By making sure it is forced to being a double, which is basically a float, it maintains the actual 0.2, 0.4, etc. And then we just take this output and plug that into NB and the out here into our output. So now before I plug this in, I'm going to do an attribute partition, and I'm going to partition it based on the index. So over here, instead of index 0 being last, I'm going to select index here. And this makes every single point go in through this loop by itself. Then I plug this into our in, and then the number of points we need to get from the room sizes. So from the room sizes, just like we did in here, we need to get the property from object path and the entries count. So I'm going to go ahead and copy this. I'm going to paste it right in here and plug our room sizes into our get property from object path, and this get entries count can go into our number of points. Now, if I sample this, you can see that all of these have slightly different values. And if I go ahead and change the seed of this, you could see that no matter what, even when it picks new points, there's always going to be a 0.2, a 0.4, a 0.6, a 0.8, and a 1. Now, the one that is invisible right now is our 0 density, and that is fine. We don't need it in this selection, but anything that's basically not selected is a 0. So now we want to go ahead and take these points and grow them based on the selection size on our original points that we actually had the wall size for, right? Because these points are very far apart. We don't want to grow based on its distance, but the original ones. And we'll do that once again by creating more loops. And what we're going to need to do is loop on the points and loop on the centers, because these center points, the 5 points that we've created, also need to be looped on. So in this scenario, we're going to be putting a loop inside of a loop. So in our loops folder, as before, we'll make a PCG graph. I'll call it PCG expand point selection, and I'm going to duplicate it and just immediately call it expand point selection underscore inner loop. I'll open both of them up and we'll set up the regular one first. Our output for the regular one will be a point and of type normal. And for the input, we're going to have a point set to loop, a center set to also point and unnormal, and a wall side set to attribute set normal, as you see right here. I'm going to open up our interior loop, and we're actually going to just reset that up. It's pretty much going to be exactly the same. The main difference is on the inner loop, we want to loop on the center. We don't want to loop on the points, because in this one, we're already doing that. So instead of the regular one, so we don't get confused on it, we'll drag in the inner loop here and create a loop node. So now we can just go ahead and drag all of these right through and plug this into our output. So that's all for this. It's basically going through all the point loops, and for each one of those point loops, it also goes through the center points. Let's go back into our inner loop now, and now we can set up this guy. So what we effectively need to do is go through all of our points and see, hey, is it nearby one of our actual points that we have isolated? Is it within this range? Yes. Set the density accordingly, and if not, it doesn't matter what you do with it. Go ahead and move on to the next one. But if it is matching, go ahead and just take the density of that point that it matched to and just set it to be equal to yourself. Because we already set those individual points to be the right density, we can just copy the density off of it instead of having to recalculate all of the densities at this point in time, which is a little bit easier. So to make sure that it's in range, out of our points, I'm going to drag out, I'm going to search for an attribute filter range, and we want put in a minimum and maximum. Now the target attribute here, instead of last, we want to select position because we basically want the location of it to be equal. And now we can go off of the center loops and get all the math we need. So from here, we can go ahead and grab ourselves a get attribute from point index. The attribute that we're going to need to get is the position of it, because that's the thing we need to be relative to. And we also need to get the half width and the half height that we created before. So I had duplicate the get attribute from point index, plug the center ones in here because that's where the information is. In the first one, I'm going to type in half width, and the second one, we're going to do half height. And make sure this is all spelled the exact same way you had it before, spaces included. And because these are in the module count department, instead of the actual distance, I'm going to go ahead and take this and now multiply both of these values by our wall size. So I'll go ahead and plug in the wall size into B here for both of these, just like so. Now from here, we basically have an X and Y, but we don't have a Z. So what we can do is right click and search for make vector attribute, convert the output type to a 3 variable. So we have X, Y, and Z. The top one, which is our half width, can go into the X. The bottom one, which is half height, go into the Y. Now, if you got these reversed, if you put, for example, the half height into the X, half width into the Y, that is completely fine. Because remember, it doesn't actually rotate. So if you go ahead and plug them in backwards, just keep in mind which one's the X axis, which one's the Y axis for your own self. But now we can go ahead and offset this from the original position. So from the original position of the point, I'm going to grab ourselves a subtract node as well as an add node. And we're going to subtract and add this little offset from the original point. So whatever this distance was that it calculated, it's just going to basically give it a range now. So this subtract will go into the filter min and the add will go into filter max. Now, if it's not in the filter, I'll go ahead and output it basically just straight out. But if it is inside the filter, we want to set the density. So inside the filter, I'll search for set and get ourselves a set node here. The input source 1 will be our density because that's the part we're going to be setting. And we're doing it again based off the center. So I'll get another get attribute from point index. I'll duplicate it up, grab ourselves the center and plug that in. And instead of position this time, we're going to grab its density. And that density is going to go right into in B. And then this whole thing gets outputted to the end. So let's go ahead and set up this loop in our main graph. I'll drag in our expand point loop selection. Make sure it's selected as a loop when you drag it in. Our points are original spline points. That loop goes in there. The center goes from the bottom, and the wall size is our wall size. We'll grab our wall size from over here, duplicate it, and plug it in. Now, before I sample this is all sorts of amount of points. If I press A and select our second building here, you can see it has all these points all separated out. So let's clean this up because it also has unnecessary points. I'm going to go ahead and merge points to make them all together. And then I'm going to do a self pruning. Now I want a comparison to be our density, and I want it to be large to small with a 0 radius similarity factor. And now if I go ahead and sample this, you could see right here, we're getting different densities of points. And if I change the seed here, you could see a little more clearly in this version where we have this being all together. This is its own thing, and each one is different. The only one that might repeat is the black, because that is the parts where that didn't get covered by a room, which again, I'm going to call it the hallway in quotes. Depending on the size of the room, of course, you'll have bigger or smaller areas. So that's up to you to configure in your data asset. And the reason we're pruning from density large to small is because we actually outputted all of the points multiple times based on the densities. And we really are only keeping the largest densities and then removing anything else. which is why some rooms have priority over others when you actually create the system. But this is very good information. In fact, we're going to be needing it at some point in the future. So from here, I'm going to drag out and get ourselves a named reroute declaration node. I'm going to press F2 to rename it, and this is going to be our room densities. We're not going to need it right now, but this is a very good node that we're going to need later on. The next thing we need to do is, now we have the densities, is create the actual walls for that. Now in our walls section, we've already created this node and this setup. So I'll go ahead and grab our create walls section with our wall size and wall thickness. I'll go ahead and copy it, plug it down right here and plug it in. And if I sampled the walls now, you can see we now have all of these extra points on the round. Now keep in mind, for some reason, this is a bug where it shows you these as well on the inside. But if I just grab ourselves a random point, like a transform points node, and I sampled that instead, you can see we're left with just the actual outline of these points, which is all we need. If you want to play around with this setup for yourself, it is available on my Patreon as always, where you can join these wonderful people right here in supporting what I do. It means a lot. And if you'd like to join the community, the link to the Discord is down below as always. Thank you again so much for my patrons. Let's get back to it. But at this point, we actually need to get our actual doors and interior walls plugged in. We need to start actually using the information from it. And to do that, we just need a couple more inputs for our data asset. So here on our PDA building that we have before set up for regular walls, detail walls, etc., we just want to duplicate one of these and call one of them doors and one of them interior walls. They're all going to be erased and they're all going to be exposed as all the other ones. So it's very simple to just duplicate it. And then when you open up your data asset, go ahead and plug in your wall piece and your door piece, right? Like I did, like so. Of course, plug in whichever one you want. The one thing to note is if you're using the Megascans ones like I am, for this door piece, the pivot is kind of in the front, which does cause some issues. So what I've gone ahead and did is just move the pivot here into the back. That way, if I wanted to, I can just go ahead and mirror it onto the other side without having any kind of overlaps to make it a little bit easier for myself. And that's the one I have plugged in into the doors here. And the wall is just a simple wall, again, all from Megascans. Now, I have checked on the open back because they don't have a back piece and we'll be filling that in. But that's pretty much all we need here. And then we want to grab ourselves a difference node and we want to cut out the actual outside walls. This is future me after actually recording the thing. The match and set node that you see that I have plugged in right after the create walls, you can go ahead and ignore. It is not needed. I've removed it, but just so you know, everything's fine. It is not necessary. Now, we don't have a reference for that, but here in our walls section, we do have the output of the static meshes, which is exactly what we need. So I'm going to take both of our static meshes and use a merge points node to merge these things together. And then from here, I'm going to grab ourselves a named reroute declaration node, press F2 to rename, and this is going to be our exterior walls. Now, going back down here, I'll go and grab our exterior walls. We're searching exterior walls, plug this in directly, and then change the difference node from minimum to binary, and go ahead and sample it. And one thing you'll quickly notice is it's also removing the point here. And we actually want this point because that means this wall does not exist. And the way we get around this is by modifying the extents of this exterior walls. So before the differences, I'm going to plug in a node called extents modifier. And basically, I'm going to shrink it in X quite a lot, but keep it in Y and Z, X being the actual length of it. Instead of set, I'm also going to change it to multiply, because whatever it was before, keep the height and the width, the thickness, but really make them narrow. And then I'm going to plug that into our differences. And if I look at it now, you can see that the points that were here are gone, but we now get that point back that we needed, just like that. Again, it goes right up to the edge, but again, all of the points that would be here on the outside, for example, for this room here, are not there, which is exactly what we want. The next thing we need to do is take all of these points and pick some doors. Effectively, we want at least one door for every one of these rooms. Now, with this setup, we can actually control how many doors we want, and we can even randomize them out. So in my case, I'll be showing you how to randomize so you know how to do pretty much all aspects of it. And if you want to, you could, of course, expose it to your blueprint so you can control the amount of doors per room. By the bare minimum, it'll always have at least one. To do that, we'll need another loop. So let's go ahead and create a new PCG graph. For that, I'm going to just call it PCG wall door split, because we're going to be splitting between two outputs. And just like before, I'll take it, drag it in, and create a loop node, and then open it up. For the input, we're just using points, and we're looping on them. And for the output, I'm making it just two sets of points, one for walls and one for doors, both set to points. So effectively what we need to do is go through all of the densities on every single floor, and then pick 1, 2, or however many we want, and make those a different output because those are the ones that are going to be doors instead of walls. So we're going to grab our points and grab ourselves a density noise, which as before is just an attribute noise set up for density. And we're going to sort it by density using our sort attributes, set for input source density. And now we want to use an attribute filter. And this is going to be a regular attribute filter instead of in range. And for our attribute filter, you want to make sure that it is set to less than, and the target attribute is index, just like we did before. And what we need to do is basically get our original points, get ourselves another attribute noise from our input, but this one's going to take our density and output it to a different output. Instead of source is going to be door count is going to be our output target. And here is the noise min and max. So this is where we control the amount of doors. If I made this between 1.5 and 2.5, it seems to always round down. So if it picks a value, let's say 1.8, it will have one door there. If it picks 2.1, it'll have two because it's in the above 2 range. So you can hard code this with the create attribute and always have to be 1 or always have it to be 2. Or you can use this, which is like a simple noise, to randomly pick between 1 and 2 doors per room. Now in my case, I want slightly fewer double door rooms than there are single ones. So I'm going to put 2.2 for the noise max and 1.0 for the noise min. So more often than not, there'll be 1 door per room. From this attribute noise, we can go ahead and get ourselves a get attribute from point index. And then we need to get this door count output that we created. So go ahead and copy it, grab ourselves the door count into our input source, and this attribute will be our filter. Now, if it's inside the filter, it's actually the doors. And if it's outside the filter, that means it's the walls. That is all we need in this loop here. So now what we need to take is our original points that we have, split it up by floor, and then split it up by the density on that floor. Now, the nice thing I learned is you can actually partition a partition and it actually works out. I didn't realize it was going to work out, but it did, and I'm very glad it did. So what you do is from this difference, you grab yourselves an attribute partition, and the thing you want to partition is basically position. So you can select position, but you want a position.z. So it splits it up by the floors vertically. And then we want another attribute partition, and the second one, instead of position, we want it based on density. We'll plug the first one into it, and then the output of this will go into our loop. Now here you could see here are the walls with a few pieces here and there missing. And if I sample the transform points that are coming out of the doors, you could see we're getting all these pieces and they're all of different densities, which is perfect. So now we want to scale these points to their actual respective mesh. And we created a setup for that, scale wall size. So I'll grab the one from the walls because it has the 2 inputs, nicely convenient for me. I'll take all of this and go ahead and duplicate it, plug in the walls into the top one, and the doors into the bottom one. For the top one, instead of detail walls, we want to change it to interior walls. And for the bottom, instead of regular walls, this is going to be our doors. And everything is kind of set up. Now, the one note here is this wall thickness. You might want a separate thickness for your interior walls / exterior walls. If you do, this is the place to do it. And this is the place to customize it. So if you wanted really thin walls and maybe thicker doors, etc., this is where you adjust that. You can in fact even have a separate value for one versus another between the doors and the walls. In my case, I'm going to keep it all consistent and together. But now that we have this, we can go ahead and take these points and just merge them all together with a simple merge points. And now one more time, we just need to remove the actual original outside walls. So I'm going to get ourselves an extents modifier, set it to be multiply with the x at 0.7, and then grab ourselves a difference node using the exterior walls that we have actually set up just earlier in this tutorial. Make sure the difference is set to binary. And now if I sample it, you can kind of see the placement of the walls. You see none of them are on the outside. This is all good. And this is here to grab any kind of stragglers that might have been missed. Then I go ahead and grab ourselves a merge points node and a simple self pruning node. So that way we go ahead and clean this up. In a self pruning, instead of large, small, I just want to remove duplicates. If there happen to be any points left over that are kind of on top of each other, let's go ahead and remove them. And now the last thing I want to do here is the transform points. Because of how we set it up previously, the actual creation of the walls, we've pushed the points out a little bit. We want to pull them back in. We want to pull them back in basically of the width that they are actually offset towards. So in the transform points, I'm going to drag out an offset min, grab ourselves a make vector vector attribute, plug that into offset max as well, and change that to a vector 3. Because we only want to offset into the Y, which is kind of the back and forward instead of side to side or up and down. And the thing we're going to need is the wall thickness. We're going to grab that, and we're going to multiply it by -1 using a create attribute. Set it to be -1, and plug that into the Y. And we're basically offsetting everything, just again, negative into the Y to put it back to kind of where it needs to be. And that's pretty much all we need here. Only thing that's left over is kind of to grab our open and close back walls and our offset transform and maybe our static mesh spawner from here. Take all of this, duplicate it over, plug in the open back walls, plug in our static mesh spawner, which in our case is already set to attribute and mesh. If I look at this, you can see that yes, there are doors and everything, but they're a little bit too far apart, including the actual walls here. That's because we originally hard-coded the offset here for the exterior windows, which don't really work here. We really don't need any kind of offset here. And that's this close open back wall. So if we open it, in this transform points, we have an offset here of -50. And what I want to do is actually go ahead and customize this. So I'm going to open this up, and in the offset min, go ahead and grab ourselves and make vector attribute, plug it into offset min and max, change the output type to a 3-point vector. And the input, I want a new input. The type is going to be an attribute set, and this is going to be our offset. And this is going to be plugged into our Y. Now, a lot of things have now been disabled. That's because I've made this offset required. As I mentioned, everything is being set to required. So this offset, I'm going to drag it here and search create attribute. I'm going to just have it be 0. But I'm also going to take this create attribute and duplicate it over here for the walls. And this one is going to be at -40. Plug this into the offset here and here. Same thing for the doors for the exterior walls. And now you can see everything lines up quite nicely, as you see here. And if I wanted to, I can go ahead and sample the self-pruning right before the room densities node. And you can see every single one of these actually has its own density in its own room. And if I want to, I can go ahead and change the seed. And you can see we get a new layout every single time. And if I go down below, go into unlit, you could see every single floor is different. Now, one last note, in case you are following me exactly how I'm doing this, I did make a few small little changes to customize it for myself over here on the room sizes. I made it 2x3, 3x2, 5x2, 4x5, and 3x5. Again, if you customize this, in fact, we can just go ahead and do that dynamically right now. For example, this 3x5, I make it 3x4. You can see immediately we get a little bit of a room there. If I make it instead of 4x5, 4x3, you can see a little room changed over there. Again, instead of 5x2, 3x2, we have a bit more room here. So as you can see, you can quickly fiddle around with these to get the values you kind of want and the result you want. There's still a few little things that I want to change and a little few things to make it a little bit better and a little bit cleaner. And we might be doing that in the future. But for now, we have interiors with actual individual densities, which is pretty freaking awesome. Now, I use a lot of loops for everything that I'm doing here. And if loops still don't make too much sense to you, including how the attribute partition works and things of that nature, check out this video right here where I explain to you just how loops work and almost everything about them.